2014 was a big year for imaging, as some of the most popular stories on photonics.com focused on new techniques to probe deeper into tissue and capture ultrafast phenomena. We'll revisit some of the highlights this week on Light Matters. This is Light Matters for December 31st, 2014. I'm Justine Murphy.
And I'm James Lowe. As managing editor for photonics.com, I keep a close eye on what our online readers are interested in. And in this year, they flocked in greatest numbers to stories about imaging, particularly for biomedical applications.
This week on the show, we're taking a look back at some highlights from 2014. But first, we continue our preview of the 2015 Prism Awards with information about the finalists in the imaging and cameras category.
The Peregrine 3D Flash LiDAR vision system from Advanced Scientific Concepts of California is used for collision avoidance, mapping, and surveillance in unmanned aerial and ground vehicles.
The OHC-15L from Espros Photonics in Switzerland is a hybrid CCD and CMOS chip with backside illumination for detection into the near-infrared.
And Raytheon's Seek Thermal smartphone accessory allows users to see energy loss and water leaks in homes, clogs in pipes, and people and pets in total darkness.
The Prism Awards are presented annually at Photonics West by SPIE and Photonics Media. They recognize innovative light-based technology products that solve problems and improve quality of life.
Tune in next week to learn about the finalists in the industrial laser category. You can also find out more at photonicsprimawards.com. Photonics must have been on the minds of the judges at the Royal Swedish Academy of Sciences this year. On October 7th, the organization awarded the Nobel Prize in Physics to the inventors of the blue LED, which for 3 decades was the missing piece in the puzzle of aesthetically pleasing white LEDs.
Back on the imaging front, the Royal Academy the next day awarded the Nobel Prize in Chemistry to 3 pioneers of super-resolution microscopy, which starting in the mid-1990s allowed researchers to visualize biological processes at the molecular level.
Diffraction makes it impossible for standard optical microscopes to image objects smaller than about 200 nanometers, but super-resolution provides some creative ways around this limit for bioimaging.
Stefan Hell, director of the Max Planck Institute for Biophysical Chemistry in Germany, was recognized for developing stimulated emission depletion microscopy, or STED, which uses one laser beam to excite and another laser to suppress fluorescent labels in biological samples, meaning light emanates only from precise points. Hell was also recognized with the Kavli Prize in Nanoscience in September.
The Nobel also went to Eric Betzig and W.E. Murner. Working separately, they developed single-molecule microscopy. This technique relies on turning individual molecules' fluorescence on and off. The same area is imaged multiple times, with just a few interspersed molecules allowed to glow each time. Superimposing these images yields a dense image with nanoscale detail.
Betzig made headlines earlier in the year for his team's work applying adaptive optics principles to subcellular microscopy. I described this research back in April. A new adaptive optics approach can sharpen microscope images for biologists studying the zebrafish. The technique, developed by a team at the Howard Hughes Medical Institute's Genelia Farm Research Campus, rapidly corrects for distortions in transparent, non-scattering tissues at the millimeter scale without exposing them to damaging levels of light. The researchers use this new technique to bring into focus the fine branching structures and subcellular organelles of nerve cells that are deep in the living brain of a zebrafish. Without adaptive optics, such structures remain blurry and indistinct under the microscope. The technique involves 2-photon excitation and takes its cues from laser-induced guide stars used to correct for atmospheric turbulence in astronomy, as well as descanning methods used to average out motion-induced errors in retinal imaging. The researchers shined their own type of guide star across areas of tissue, and the returning light was analyzed by a wavefront sensor to determine what optical corrections were necessary. The adaptive optics compensated for spatial variation in aberrations and recovered diffraction-limited imaging over large volumes, more than 240 millimeters per side, with a 14-millisecond update rate. The research was published in Nature Methods.
In March, former editor Laura Marshall described the significance of another new imaging technique based on Raman scattering.
A new optical imaging platform allows scientists to visualize small biomolecules inside living biological systems with minimum disturbance. This represents a significant step toward a long-standing scientific goal. A team at Columbia University has developed a general method to image a broad spectrum of small biomolecules, such as molecular drugs and nucleic acids, amino acids, and lipids, for where they are and how they function inside cells. The researchers coupled the laser-based technique SRS microscopy with a small but highly vibrant alkyne tag. This new technique obtains high detection specificity and sensitivity by SRS imaging. The unique stretching motion of the carbon-carbon bond that is carried by the small molecules produces a 3D map of them inside living cells and animals. The researchers plan to apply the technique to other biomedical questions as well, including detecting tumor cells and probing pharmacokinetics in animal models. The research is published in Nature Methods.
Two popular stories this year focused on techniques for visualizing ultrafast laser pulses in slow motion. In November, we spoke with Dr. Yuri Stepanenko of the Polish Academy of Sciences, who worked out a way to turn sequential images of multiple pulses into a composite movie of a single beam virtually creeping down a hallway.
Then came the news about another technique fast enough to track one pulse at a time, which I described in a clip from earlier this month. A modified streak camera is fast enough to capture the movement of a single laser pulse in real time. A team at Washington University in St. Louis has developed a 2D streak camera capable of imaging events at up to 100 billion frames per second, enabling temporal resolution in tens of picoseconds. They used the device to make a slow-motion movie of a pulse refracting at the interface between two media, two different pulses racing in different media, and to study the lifetime of a fluorophore used in bioimaging. The Washington University device is about 4 orders of magnitude faster than the fastest CCD and CMOS systems. The streak camera features a wider aperture than most streak cameras to allow 2D imaging, and a pair of electrodes that cause different parts of the signal to hit the sensor at different times. The setup also features a digital mirror device to encode the information. Lead investigator Dr. Li-Hong Wang said he thinks the technique, called compressed ultrafast photography, will enable discoveries that haven't even been thought up yet. The research was published in Nature.
Thanks for joining us for this look back at some of our top stories of 2014.
Until next week, from all of us at Photonics Media, we wish you a happy new year of light.